Okay, so it's 6 o'clock and hopefully everything's working and we're ready to get going. Um, almost. So this is going to be a full rundown of everything that could come up in the paper, including some maths bits and some working scientifically bits, but I'll leave them until the end so we can start off with all the physics first.
You are going to be given a copy of the physics equation sheet, but that only contains each equation in one format, and it's extremely likely, particularly if you're sitting the higher tier papers, that you'll need to solve some of these equations for different subjects, either by rearranging or by substitution. So if you're not very confident with rearranging, it might be worth memorising some of them in their rearranged formats. The equation sheet also doesn't tell you what any of the units for these quantities are. It's a good idea at the very start of your exam, before you start looking at the questions, to write down what these units are. You should know that all forms of energy are measured in joules, and that includes work done, which is just another type of energy. Mass needs to be measured in kilograms. This is one of the most likely quantities to be given to you in a different unit. It's really likely that AQA will write a question with the mass given in grams, and then you need to convert to kilograms by dividing by 1,000. Speed is in meters per second. Height and also extension are in meters. And gravitational field strength is in newtons per kilogram. Temperature change is in degrees C, and specific heat capacity is in joules per kilogram degrees C. That's one of the harder units to remember, but if you know the other quantities for that equation, then you can work it out because it's just a compound unit. Time always needs to be measured in seconds, and power is in watts. Then we've got charge flow in coulombs, we've got current in amps, potential difference in volts, because of course the other name for potential difference is voltage, and resistance in ohms. We've already covered all of the quantities for the first two of these equations, but then we get to density, and this is a tricky one because it's one of the only examples where the exam board might ask for your answer to be given not in standard units. So the standard units for density are going to be kilograms per metre cubed, and that comes from a mass measured in kilograms and a volume measured in metres cubed. But it's also possible that the exam board could give you the mass in grams and the volume in centimetres cubed, and rather than asking you to convert those, just ask you for the answer in grams per centimetre cubed, because it's just a compound unit. Then we know that specific latent heat is in joules per kilogram. And finally, just for the triple scientists, we have pressure multiplied by volume is a constant, and the pressure is going to be measured in pascals, and the volume again needs to be in metres cubed. The first topic in GCSE Physics Paper 1 is energy. You should know that a system is an object or a group of objects. A system can store energy, and there are 8 different ways that it can be stored. It could be a magnetic store, a kinetic store, which means a moving object, a thermal store, so a hot object, a gravitational potential store, where an object has been raised against the action of a gravitational field, a chemical store, where the energy is stored in chemical bonds, an elastic potential store, where an object has been stretched, an electrostatic store, where we have attraction between positive and negative objects, and finally a nuclear store. It's possible for energy to be transferred between those 8 stores in 4 different ways. By heating, due to a temperature difference, mechanically by forces, electrically, and by radiation. You can't store energy as a light or a sound, but you may have energy being transferred through radiation, of which light and sound are types. It's possible for energy to be transferred between those stores in 4 ways: by heating, because there's a temperature difference, mechanically, electrically, and by radiation. You can't store energy as a light or a sound, but you may have energy being transferred through radiation, of which light and sound are types. The law of conservation of energy says that within a closed system, energy cannot be created or destroyed. It can, however, be transferred between different stores. So this might mean that we start out with a chemical store and finish with a thermal store, but the total amount of energy is the same. A closed system is a situation where no matter and no energy can get in or get out. Energy is always measured in joules, and you need to write joules with a capital J. If a gravitational field is pulling an object down towards the centre of the Earth, and instead we raise that object up in contrast to that gravitational field, then the object becomes a store of gravitational potential energy. You're expecting to see lots of questions in GCSE Physics where you're asked to use one of the equations from the equation sheet to calculate the amount of energy. So to calculate gravitational potential energy, we would multiply together the mass, the gravitational field strength and the height, being careful, of course, that all of these need to be given in the proper units. So if a question asked how much gravitational potential energy was transferred to a 5 kilogram dumbbell when it was lifted by 150 centimetres, firstly, I'd need to know the gravitational field strength. And if you're doing combined science, then you are going to be given that value. I'd also need to watch out for the fact that the height here has been given in centimetres, so I would need to convert it. Once I've done this, I can substitute in all of the numbers from the equation, and then I can multiply those together to get my answer, which is 73.5 joules. And of course I want to give the units, and of course I need that J to be a capital.
So I've got a couple of people asking about it being live or not. Yeah, hi, I'm here, but I just can't respond to you when I'm in the middle of a slide because I'll lose my train of thought. So I'm only looking at my phone very periodically, and hopefully that way I can stay on track and actually do it in the right amount of time. But feel free to put questions in the chat because I am keeping an eye on it, and you know, I can reply to things when I get to the end of a particular slide. So yes, static electricity is going to be covered in the electricity topic, don't worry.
The next energy store is kinetic energy, which is where we have a moving object. Things to watch out for with this equation are that the squared sign only refers to the velocity. It's not everything before that that's being squared. A typical question might ask you how much energy has been stored. So again, you'd pick the equation from the equation sheet and write that out, and then you would substitute in the appropriate numbers from the question. If you don't have a fraction button on your calculator, then it's fine, you can just use 0.5 instead. I would multiply those numbers together, making sure that I'm only squaring the 5 and not everything else, and that would then give me an answer of 250 joules. The elastic potential energy equation also has a squared sign, and again it only refers to the final letter. And here you need to watch out for the fact that the extension needs to be in metres in order for the calculation to give the correct answer. If we were asked to calculate one of the other terms, such as spring constant, then you can either rearrange the equation or substitute. Both methods are creditworthy. This question asks me to calculate spring constant. So you could take that equation, double everything to get rid of the half, and then divide both sides by the extension squared, but also you can just substitute in the numbers and work it out as you go along. So here we could say that the energy is 4,500 joules, and then we're doing half times by k times by 3 squared. So that tells me that 4,500 is equal to 4.5k, and then if I divide both sides by 4.5, I can figure out what k is without ever needing to rearrange my equation.
Okay, so there was a question about whether you can use speed instead of velocity and just use them interchangeably. And for everything that you're doing in Physics Paper 1, yes, you will be able to. Obviously, we know that velocity is a vector quantity, so it has direction. But in terms of all the calculations that you're going to do in paper 1, it's not going to make a difference. We're really going to start worrying about it when we get to the forces topic in paper 2 and thinking about things like acceleration and momentum. Then it's going to be more important. But for the sort of thinking about things like calculating kinetic energy, it's not going to make any difference.
The next topic is specific heat capacity, which comes up in two different parts of the specification. Capacity is all about the ability of an object to take something in. So then heat capacity is about the energy that a substance absorbs when it's changing temperature. And specific heat capacity is the energy that 1 kilogram of a substance needs in order to raise its temperature by 1 degree C.
So as far as methods go, what I would suggest, I've got a whole video series called the 6-mark challenge. So that's all, it's about 79 videos, I think, that I've done, which are model answers to extended response questions. And I think pretty much all of the required practicals are covered with those. I find most people just get a bit bored if I'm just putting up these are the steps for the required practical, but I have got all of that on the channel if you just search for 6-mark challenge.
In order to carry out the required practical, we're going to need to do some calculations of specific heat capacity, and for that we need this equation. Now this one is often a little bit intimidating to people because there are some extra symbols. So this triangle sign is called a delta sign, and it's the sign for a change in something. So delta E isn't two different things that have been multiplied together, it's the change in the amount of energy that's available. And it's measured in joules because, of course, it's energy. And then likewise, this delta theta on the right-hand side, that's the change in temperature. So, of course, it's measured in degrees C. Then we've got mass in kilograms. And then the tricky one is specific heat capacity. And this is going to be measured in joules per kilogram per degree C. Just like density and speed, this calculation is actually quite a nice one because the units for the tricky bit actually tell you what to do with the calculation. Say if we wanted to calculate specific heat capacity with that as the subject, if you take the units, you can see that we've got the amount of energy in joules divided by the mass in kilograms and the temperature in degrees C. Also, watch out for the fact that you do need to have the change in temperature. So you could be given a starting temperature and an ending temperature and need to work out the difference. The idea of the required practical for this topic is that you're given either a metal block or a container of liquid, and you're trying to work out what the specific heat capacity of that block or that liquid is. In other words, how much energy would it take to heat up 1 kilogram by 1 degree C? Firstly, you're probably going to have a metal block with 2 holes in it, or you might be given a beaker of liquid. You have a balance because we want to know how much energy it takes to heat up 1 kilogram, and your block might not have a mass of a kilogram, so we would then need to adjust our calculation to take account of that. There's some insulation because the experiment will only give us accurate data if all of the energy that's transferred by the heater is going into the block or into the liquid. Now obviously that's not realistic, and some of it is going to dissipate and go into the surroundings, but we want to minimise those energy losses as far as possible. We have a thermometer so we can identify how many degrees the object has been heated up by. And realistically, we're not just going to heat it up by 1 degree C, because making really small measurements reduces the precision of the final value. So to increase that precision, we're going to heat the block up by maybe 10 or 20 degrees and then divide the amount of energy by 10 or 20 to take account of that. The pipette is here because the thermometer won't make good contact with a metal block. So in order to get an accurate temperature reading, you add a tiny bit of water and that will come up to temperature with the block. And then what you're really doing is taking the temperature of the water. We need some kind of electrical heater to heat up the block. And then the last 3 pieces of apparatus are for us to calculate the amount of energy that's been transferred. So you measure potential difference using the voltmeter and current using the ammeter. And then those 2 readings together can be used to work out power. And then once you know the power, you can use the stop clock to work out the amount of energy transferred.
So for the people in the chat worrying this doesn't look like triple content, firstly, I'm a little bit concerned that you don't realise that everything I've said so far is in the triple exams as well. So there's nothing in combined science that you don't need to know for triple. But also up the top where it currently is saying, well, currently it's not saying anything because I've taken my slide down, but it's currently saying something like Unit 1, energy. When it becomes triple only content, that bit goes bright purple, and somewhere over here it says triple physics. And that's the point where the combined scientists know that they don't need to know about that. But everything that is for combined science, you do need to know for the triple exams as well. There's nothing that's combined science only.
Joule meters aren't mentioned anywhere in the specification, but they were considered credit-worthy in the 2022 exams. So you could probably describe just using that piece of equipment, which will directly read you out the amount of energy transferred. The final topic in this 1.1 energy section is power, which is the rate at which energy is transferred or work is done. In other words, how quickly does energy move between different stores? The more powerful an appliance is, the faster it can do work or transfer energy. Typically, quite early in the GCSE Physics paper, you might be asked to calculate the power of an appliance such as a kettle transferring a certain amount of energy in a certain amount of time. So here I would say that the energy is 2000 and I divide my answer by 4 because that's the time in seconds, and I get an answer of 500 watts. Now you'll notice here that to get my answer, I calculated energy in joules divided by time in seconds. So we can also describe a watt as a joule per second.
So for the specific heat capacity required practical, there's just been a question about do you need to know it with oil instead of a block? It's just the same practical. The only difference is that you have a beaker full of a liquid instead of a metal block. So you would put a beaker on a balance, measure out your oil into it so that you know how heavy that oil is, and then it's just exactly the same practical. Also, there was a question about what about foundation? So far, everything that I've covered is foundation tier as well. So there is also a colour change at the top of the screen when it gets to higher tier, but there's actually surprisingly little higher tier only content in Physics Paper 1. It's pretty much just a split of combined science versus triple. And in answer to a couple of other questions, 30% of the paper is math skills. So that has to be stuff that is hard enough to be on a GCSE maths paper at least foundation level. Or if you're taking the foundation exams for science, then stuff that's hard enough to be in Key Stage 3 maths. So that's not just calculations, that's also things like plotting data from graphs, reading data from graphs, yeah, lots of different math skills. But it also means there are some things that are calculations, but that aren't counted towards that because they're basically not hard enough. So if you were adding up some numbers, say, that wouldn't count towards the math skill quota.
Efficiency is the proportion of energy that's usefully transferred, and it can be expressed either as a decimal or a percentage. The law of conservation of energy means that my useful and wasted energy transfers must add up to be the same as my initial starting amount of energy. Here, my light bulb might transfer 1000 joules of energy, but 100 joules of that energy is transferred as light radiation, and the other 900 joules is transferred wastefully by a heating pathway. So my light bulb would only be 10% efficient. Or we could also say it has an efficiency of 0.1.
Yes to math skills at the very end, just because I found with with the biology that people were kind of going, I don't want to know about math skills, let me get onto the biology. So I thought I'd do the physics first, and then at the very end we can do final reminders, working scientifically, different variables, math skills, and people who just wanted the physics can sort of leave.
There are two equations for efficiency, but the only difference between them is that one of them is expressed in terms of energy and one in terms of power. If a question asks you where the energy ends up when it's wasted, there will almost always be a transfer to a thermal store in the surroundings, and when the energy has spread out so far that it's not useful anymore and we just can't use it, we describe that as dissipating. This is our very first higher tier only slide, so it's for both combined scientists and triple scientists, but only if you're taking the higher tier. In that case, you need to be able to discuss a number of ways in which we could reduce wasted energy. That could be reducing heat loss by insulating something, which is particularly relevant if you're thinking about houses, which might have loft insulation or double glazing. We can also talk about the thermal conductivity of a material. If you compare building materials like regular brick versus breeze block, then the higher the thermal conductivity is, the higher the rate of energy transfer by conduction. So in other words, the better conductor, the faster it conducts. You can also reduce wasted energy by reducing drag, by streamlining, which is particularly relevant if you're thinking about vehicles like boats or cars. We can also reduce wasted energy by reducing friction, which might be by using wheels or lubricating moving parts. If those frictional forces aren't reduced, then they can cause energy to be transferred by heating.
Right, time for a brief water break. And double checking the chat, which I said I wasn't going to do in between times, but I have got suitably distracted. I think we are pretty much up to date with commentary things. Approximately when will the session end? If I did it all without breathing, then I would get through it by 7 o'clock. I keep pausing to look at the comments, so I guess maybe 7:15. It shouldn't be too long, but I'll be hanging around online afterwards if people do have specific questions.
The next required practical is only for people sitting GCSE Physics or triple science, and it's really quite similar to the practical that everybody does as part of the waves topic for paper 2, where you're investigating different materials. So here we're looking at the effectiveness of different materials as thermal insulators. You start out with a series of metal cans or hollow metal cubes, and these need to have the same dimensions and be made of the same material. So these are going to be control variables. But they're going to differ in the type of insulation that you wrap around them. You might also include one can that doesn't have any insulation at all, and we would refer to that as a control. Don't mix it up though with control variables. So control variables are things that are the same for every single experiment, whereas a control is something where we haven't applied any insulation at all. You're going to fill each of the cans up with hot water, and the volume of water would be another example of a control variable. So we'd probably discuss measuring this out with a measuring cylinder. Then we're going to put a thermometer into each can and wait a little bit for that thermometer to show the highest temperature that it can, because it's going to take it a little while to sort of acclimatise to its environment. Then when you see the temperature start to go down, then we know that we're ready to start the clock. So maybe every minute for 10 minutes, you take a reading and you record this. And based on this, we can see that the temperature that drops the least must be the can that is best insulated. The final part of this energy topic is about national and global energy resources. You should be able to distinguish between renewable energy resources, which are being generated faster than they're being used, and non-renewable or finite energy resources, which are being used faster than they're being generated. These energy resources can be used in a variety of ways, including transport and heating, as well as electricity generation. For each resource, you should be able to discuss the advantages and the disadvantages. This often comes up as an extended response question where you're asked to compare the advantages and disadvantages of two of these different energy resources. So you want to think about things like, are they renewable? Are they expensive? Do they produce carbon dioxide emissions, which you can link to global warming? Are they reliable? And are there geographic restrictions on where you can use them? So for instance, you can only use tidal power if you're near the coast. Then for nuclear power, you also want to think about how you would dispose of the radioactive waste and also the risks associated with nuclear accidents, both of which are disadvantages. The second topic in AQA GCSE Physics Paper 1 is electricity. The first thing you should know is how to draw all of the different circuit components. Of course, it's important that when you put these together in a circuit, you're using a ruler for your wires and you're not leaving any gaps in the wire. One symbol in particular to watch out for is the resistor, because people often draw the lines for the wires of their circuit first and then draw the rectangle over the top of that, and that would mean that you are actually drawing a fuse rather than a resistor. Also be careful that when you draw an LED or an LDR, the arrows represent light. So for the LED, the arrows are coming out, and for the LDR, the arrows are going in. There are lots of different equations for electricity, and although you are going to be given them on the equation sheet, it's worth bearing in mind that for higher tier extended response questions, you might be required to use two or more of these equations for the same question. So for instance, you might be given current, resistance and time and asked to calculate energy. And in that case, you would need to be using current and resistance to work out power, and then putting power together with time to work out energy. If you do get a 4 or 6 mark question where you're asked to calculate something and you just can't see from the question where you're supposed to start, what I would do is highlight or circle the different numbers that are given in the question and identify what quantities they are, and then look at your equation sheet and see what can you calculate, because that's almost certainly the first step and will still be worth some intermediate marks even if you can't make it all the way through to the end of the question. You should be familiar with the idea that current is the speed of the flow of charge around a circuit, and potential difference is about how much energy is being transferred by a component. Even though we now know that current in a typical electrical circuit is the flow of electrons, when the idea of electricity was first described, scientists didn't know about electrons, and so they thought that what was moving was a positive particle. So when they first started describing electrical circuits, they described current going the wrong way. And so even though we now know that it's electrons that move, we still continue to talk about this, and it's what we call conventional current. The first electricity required practical is looking at the IV characteristics, in other words, how does the current change when you change the potential difference, of a wire of different lengths, and also resistors in series and parallel. For each one of these, you need a simple circuit containing an ammeter, which needs to be in series so that it works and measures the current, and a voltmeter, which needs to be connected in parallel. If you remember, the voltmeter is measuring potential difference, and so in order to measure the difference between either side of the wire, it needs to be connected on both sides. When you're doing this practical, it's important that you don't let the wire get too short, because if you do, then the current will get really high and the wire will get really hot, and that will influence your data and also be quite unsafe. In the second electricity required practical, we're still measuring the current and the potential difference, but this time we're looking at a number of different components. This could be an ohmic conductor, in other words, a wire or a resistor at constant temperature, or it could be a filament bulb or a diode. You might be asked to draw a circuit that would allow you to complete this practical. Again, it's really important that the ammeter is in series and the voltmeter is in parallel. You could change the potential difference by using a power pack and changing it on there, but the other thing that you can do is to include a variable resistor within the circuit. And then as you increase the potential difference across that resistor, you're going to decrease the potential difference across the other component that you're examining. Once you've completed the practical, you'll be able to draw 3 IV graphs with potential difference on the x-axis, and then as potential difference increases, we see what happens to the current. An ohmic conductor, like a wire at constant temperature, gives us a directly proportional relationship, which means that as potential difference doubles, current also doubles. We can see this because we have a straight line graph that passes through the origin 0, 0.
With conventional current, it's going to be important if you're doing the Fleming's left-hand rule when you get to paper 2, but if that's not for you, then no, it's not relevant. It's just a thing that you have to know.
The filament lamp gives us this slightly S-shaped curve, and the reason for that is that the temperature is no longer remaining constant. As we increase potential difference, that increases current, and as we increase current, that is increasing temperature. As we increase temperature, that increases resistance. So even though the current is still going up as the potential difference goes up, it starts to go up by smaller and smaller amounts. Finally, we have the diode, and there are 2 important things to note about this graph. The first one is that there's nothing below the x-axis, and the reason for this is that the diode will only allow current to flow in one direction. The second thing to note is that if you only have a very small potential difference, then you still don't get any current flowing. So initially there's a little bit of insulation, and then when you give the diode a higher potential difference, then current can begin to flow. So the graph is going to track the x-axis for a little while before it goes diagonally upwards. You should be familiar with light-dependent resistors and thermistors. These graphs look similar to the previous graphs, but there are some key differences. We no longer have current on the y-axis, and instead we have resistance. What these graphs tell us is that a light-dependent resistor resists less as the light gets brighter. So you could use it to turn on a radio in the morning. As the sun comes up, the resistance goes down, the current starts to flow, and your radio switches on. And then for the thermistor, as the temperature increases, the resistance gets less. So that's the opposite of a wire. In a series circuit, there is only one path that the charges can follow. Whereas in a parallel circuit, there's a junction where the current splits. And in this example, some charges go past one light bulb and some charges go past the other light bulb. For series and parallel circuits, you need to be able to discuss both the current, so how quickly the charges are moving, and the potential difference, the amount of energy that's being transferred. If we think about the series circuit first and current, we've said that current is about how many charges pass a particular point per second, and the image you want to have in your head is that this is like a traffic jam. There are no gaps, and if one charge moves forward, the ones behind it will also move forward, and everything has to move at exactly the same speed. So because there's only one loop and all of the charges are going the same way, they're all going to go at the same speed. So if we measure the current anywhere in a series circuit, it will be exactly the same, and I can put my ammeter wherever I like. Now the parallel circuit is a little bit different because the charges are still going nose to tail like they're in the traffic jam, but when they get to point A, they're going to split. So if those, a helpful image to have is a traffic jam. In a parallel circuit, the current isn't the same everywhere. If we picture the electrons as they leave the cell, to start with they're all together. But when they reach point A, some of them are going to go into that first branch and some of them are going to carry on into the second branch. So this means that those 2 branches put together will have the same current that we could measure right to the side of the cell. In the example I've drawn here, the 2 branches are identical, so half the current would go one way and half the current would go the other way. But if we had a more complicated example with different components in the different branches, then different amounts of current would split in each way. So say if one branch had double the resistance of the other branch, then it would only have half as much current. In this parallel circuit, I don't have 2 identical branches, but I can still say that if the current directly next to the cell is 12 amps and the current in this branch is 8 amps, then the current in the second branch must be 4 amps, because ultimately those 2 currents still need to add up to be the starting current. Potential difference is all about the energy that's transferred by components. So in my series circuit, that energy needs to be split between the 2 components, and each of them, if they're identical to each other, is going to get half. But in my parallel circuit, each electron in this example is only passing one component, and so it can pass on the full amount of energy that it's able to provide. So in this example, both of my light bulbs would have the exact same potential difference. Now that same potential difference is going to be true for the two branches, but if one of my branch contained two components, then we'll be back to thinking about this in a series way. So if I come back to my circuit from earlier, if the potential difference across the cell is 12 volts, I know that every branch is also getting 12 volts. So for my first branch that only contains one component that's going to draw potential difference, I know that that's also going to be 12 volts. But for my second branch, I've then got two bulbs in series with each other. So each of those is only going to get 6 volts. Finally, if we think about resistance, you should be able to describe that in a series circuit, to work out the total resistance, you just add up the individual resistors. So if I have three 2 ohm resistors in a series circuit, then the overall resistance of that circuit is just going to be 6 ohms. Whereas in a parallel circuit, the total resistance is going to be less than the resistance of the smallest individual resistor. To actually work it out, we would say that 1 divided by the total resistance is going to be equal to 1 divided by each of the individual resistances added together. But the most important thing is that when you add up all of those together, you're going to find out that the overall resistance is less than any of the individual ones. The British main supply of electricity is AC, which stands for alternating current. This is current that repeatedly changes direction. In the case of the British main supply, this happens 50 times per second, so we can describe the frequency as being 50 Hz. This helps to maintain power and is also important because the transformers used in the national grid will only work with an AC supply. In contrast, direct current, which you get in a simple circuit with a cell or a battery, is current that only flows in one direction. In addition to knowing the frequency, you should also know that the UK main supply has a potential difference of 230, not 240 volts. Most appliances are connected to the main supply using a 3-core cable, which attaches to the supply using a 3-pin plug. The outside of the plug is made from rigid insulating plastic, and the pins are made from an alloy of copper called brass. As you know from chemistry, alloys are harder than pure metals, so this stops the pins from bending when you push the plug into the wall. You need to know the names, locations, colours and functions of the 3 wires.
Nwando's right, you don't need the resistance equation for parallel circuits. You don't actually need the equation. It's just that I tend to find that mathsy brain people don't like the idea. They're like, how can it possibly be that the resistance of the total circuit is less than any one of the individual ones? Like, it just doesn't make sense to them. So I give people the equation to be like, look, you can do the maths. This is what the number is, and it's always less. But that's not an equation that you are actually expected to use at GCSE. So don't stress about it. I'm sorry if I stressed you out by putting it in. You do need to know, with CMAT, that's all forces topic stuff, so not for tomorrow, but you will need to know speed is distance over time, because that one is not on the equation sheet. Like, the whole point is that you guys are being given an equation sheet that used to need to be memorised, but the equation for speed isn't on the equation sheet, so you need it. Can I explain why resistance is less than power circuit? Not in less than about 4 minutes, which, yeah, ask me again.
The live wire is the brown wire, and you can remember that it goes on the bottom right because bottom right is BR and so is brown. The live wire carries the alternating potential difference from the main supply. The neutral wire is blue and it sits on the bottom left of the plug. BL for bottom left, BL for blue, and it completes the circuit. It has a potential close to 0, which is earth potential. The earth wire has green and yellow stripes, and it's a safety wire to stop the appliance becoming live if there's an electrical fault where the live wire touches the metal casing. The plug also contains a fuse, which will melt if too much current flows. It's really important that you talk about it melting, not saying it blows up. A fuse has a rating based on how thick it is. Typically in the UK we use 3 amp or 13 amp fuses. You need a fuse that has a rating slightly higher than the normal current. So if I had an appliance where the normal current flowing was 11 amps, then a 13 amp fuse would be appropriate for me to use, because if there was a current surge, then the fuse would melt and break the circuit. I wouldn't use a 3 amp fuse because that would melt when the appliance was operating normally. The national grid is a series of cables and transformers linking power stations where electricity is generated to domestic customers like houses. The transformers are important because they allow this to be a really efficient process. In those central cables that run between pylons, the electricity is travelling with a really high potential difference. And the reason for that is that there are 2 ways that we can get the amount of power that we need for our domestic customers. Firstly, we could have a really high current, but this would mean that the electrons were moving very quickly, and this would cause the wires to heat up, and therefore we would lose a lot of the energy to the surroundings, where it would dissipate into the atmosphere. So high current doesn't really work for us because it wastes a huge amount of energy and therefore costs a lot of money. The alternative is to have really high potential difference, but we don't want that high potential difference in the power stations and the domestic supply because high potential difference is really dangerous. So we have between the power station and the cables a step-up transformer which increases the potential difference, and then we have this really high potential difference going through the cables, and then at the other end there's a step-down transformer which reduces the potential difference so that it's safe for consumers again. When insulating materials are rubbed against each other, they become electrically charged because the force of friction removes electrons from one and moves it onto the other. The electrons are negatively charged, so the material gaining those electrons will also become negatively charged, and the material that lost the electrons will become positively charged. When we have two objects that have different electrical charges and they're brought close to each other, they exert a force. A charged object has an electrical field, and that field is a region where if we brought another charged object, then it would experience a force. So that would be an attractive force if the objects have opposite charges, or a repulsive force if they have the same charge. This is an example of a non-contact force, so the objects don't need to touch each other. The electrical field is the strongest where you're closest to the object. You need to be able to draw these electrical field patterns for isolated charged spheres. In other words, we imagine that an object is purely positive or purely negative, and we draw the electrical field lines like they would look for that. Your electric field lines are always going to be drawn from the point of view of what would happen to a positive object. So if you have a positive object, then the field lines are going away from that positive object because they would be repelled, and if you've got a negative object, then the field lines are all going to be coming in towards that negative object to show that an object would be attracted. You also need to be able to describe sparking in terms of something like discharging a Van de Graaff generator or lightning. It's where we have an earthed conductor which approaches a charged object, and then very quickly the charges jump across the gap from the charged object to the earthed conductor, and the object discharges, and that happens in a fraction of a second.
Okay, so with the someone asked about the speed one. So you do have a version of the speed equation. Oh, thanks, Chantel. Very much appreciated. You do get the distance is speed times time, but you almost never get to use it that way around. You're usually using it as speed is distance over time. So if you're happy rearranging stuff, then that's fine. But lots of people aren't happy rearranging stuff, or like they get stressed about it in the exams. So one thing to remember is that actually AQA are weirdly like not encouraging about rearranging. They actually, all their mark schemes are laid out so that you substitute before you rearrange, which is way easier to do, and you are allowed to do that. But yeah, if you're someone who gets stressed out by remembering rearranged versions of the equations, then I do suggest just learning the rearranged versions, and that way it's a bit less stressful. Anyway, I meant to be drinking, not talking.
The third topic starts off with three states of matter that you should be able to recognise or draw. Later I've drawn these in a more traditional way where the boxes are the same size, but I don't want to give you the impression that the number of particles changes during a state change because that's not accurate. In the solid, the particles are packed closely together in a regular structure. In a liquid, the particles are still close together and touching. There aren't any gaps that are big enough to push a particle into, but the particles are no longer in a regular structure. In a gas, the particles are separated by long distances. In a solid, there are really strong forces holding those particles in place. These forces become repulsive if the particles get closer to each other. In a liquid, the forces are a bit weaker, so the particles maintain contact and they can't individually leave that bulk material, but the forces are weaker than they are in a solid. And in a gas, there are really weak forces. In fact, previous exam mark schemes have described them as negligible. In a solid, the particles are moving, but they vibrate in fixed positions, whereas in a liquid, the particles are able to pass each other, and in the gas, the particles are moving in random directions at a variety of speeds. It's difficult to change the shape of a solid because of these strong forces and because the particles are regularly packed together. Liquids can change shape quite easily if they're poured into a different container, but they're virtually incompressible. So if you put some water in a syringe, you can't squash it because there aren't any gaps for the particles to move into, and that's how hydraulic brakes work. A gas can easily expand to fill a space, and therefore it's also easy to compress the gas because there are big gaps between particles. You should be able to name all of the state changes, so melting, freezing, boiling, evaporating, condensing, and of course the one that people forget is that some things can sublime, which is where it turns straight from a solid into a gas. This is very rare, but carbon dioxide does it, and so does camphor wax. Deposition, which is the opposite of sublimating, is not named in the GCSE specification. You should be aware that in all of these state changes, there is no change in mass. This is because you still have the same particles that were there at the start. State changes are physical changes, so we're not making new chemicals, and if we reverse the heating or the cooling, then we can get back the original substance with the original properties. We can link these states of matter to density, which is a measure of how much mass is contained within a unit volume of a substance. In the vast majority of substances, the particles in a solid are closer together than in a liquid, and that means that within the same volume you're going to be able to fit more particles. And since those particles have the same mass, if there are more of them, then we have more mass per unit volume, and therefore the density is higher. If you have a metre cubed of a metal, a metre cubed of some water, and a metre cubed of some chlorine, you can see that the masses are gradually going down, and therefore so are the densities.
So half-life is part of the radioactivity topic, which is the 4th topic out of 4. So I am going to get to it, just not yet. And yes, sublimation is when something turns from a solid straight into a gas. So like if you've ever been to the theatre and seen a smoke machine, that uses pellets of dry ice, which is actually carbon dioxide. And carbon dioxide can turn straight from a solid into a gas because its melting point and its boiling point are actually the same temperature. So it basically does 2 state changes at once. So that's called sublimation. And then the opposite, going from a gas to a solid, is deposition, but you're not supposed to know about that at GCSE for some weird reason.
In the next required practical, we determine the density of regular and irregular solid objects and also liquids. The calculation to work out density is mass divided by volume, and it's one of the nice ones where the units give you the equation and vice versa. So whether we're looking at a regular solid or an irregular solid or a liquid, we need to know what the mass is, so we're going to need to use a balance. And you also need to know what the volume is, and that's where it's different for the 3 different parts of the practical. For a liquid, we're going to use a measuring cylinder. You put the measuring cylinder onto the balance and then zero it, so it's like the measuring cylinder wasn't there, and then you're going to fill up the measuring cylinder with a certain volume of liquid. And the bigger the volume is, the more precise your data will be. And then you record the mass and you read the volume from the measuring cylinder. For a regular object like a cuboid or a cube, you can measure the length and width and depth using a ruler, or to be even more precise, you could use calipers. Then you can calculate the volume by multiplying the length by the width by the depth. Or for a cube, you could just be given one length and you would use the same length 3 times. Then you calculate density by taking the mass that you measure on the balance and dividing it by that volume. To work out the volume of an irregular object, you need a piece of equipment called a displacement can or a eureka can. You fill this can up completely with water until the water is coming out of the spout. Then you put your object into the can and completely submerge it. As you do that, more water will come out of the spout, and the volume of that water will be equal to the volume of the object. So you collect that displaced water in a measuring cylinder, and then again you can measure the volume by reading it from the measuring cylinder. All objects contain a store of energy called internal energy. This is made up of 2 things: the total kinetic energy from the system, in other words the particles that are moving around, and the total potential energy of the system. As you heat a system, the energy stored within the system will increase, but this isn't always reflected by an increase in temperature. If we take some ice and we heat it up, we see a graph that looks like this. This might come as a bit of a surprise because you might expect the temperature to just go up in one nice straight line. To begin with, we have this horizontal line here where the ice is melting, and then another horizontal line here where the water is boiling. Whenever a pure substance is going through a state change, the temperature doesn't change. You can almost think of it like the substance can't multitask. Either it can get hotter or it can change state, but it can't do both things at the same time. So the red bits of the graph here represent places where the energy is going into the substance and it's making the particles move faster. If it's a solid, like ice, then the particles are vibrating faster in their fixed positions, and if it's a liquid, the particles are moving faster past each other, and so the temperature is increasing. If I want to know exactly how much energy it's going to take to heat up the substance, then we need to know the specific heat capacity, which we met earlier in the energy topic. This tells us how much energy is needed to raise the temperature of a substance by 1 degree C. Then the green portions of the graph here are where the state changes are happening. And here, instead of that energy increasing the kinetic energy of the particles, it's increasing the potential energy of the particles. And that's where my state change happens. If I want to know how much energy that's going to need, then I need to know about specific latent heat, which is the amount of energy needed to change the state of 1 kilogram of a substance. Now that's not going to be the same amount of energy for melting as for boiling, so we have slightly different names for the different state changes. We have the specific latent heat of fusion, when a substance is melting, and the specific latent heat of vaporization, when it's turning into a gas. Again, this is an equation with nice sensible units in that energy is measured in joules and mass is measured in kilograms, so specific latent heat is in joules per kilogram. We've already mentioned that the particles in a gas are in constant random motion, and also that temperature is related to the average kinetic energy of a substance. So if we're working at a higher temperature, then the particles are moving faster. Provided we're working at constant temperature, then the pressure and the volume of a gas are inversely related. This means that if I took a balloon with a volume of 1 metre cubed and a pressure of 100,000 pascals, and then I stretched out that balloon so that its volume doubled, then the pressure would halve. And if I doubled the volume again, then the pressure would halve again, and so on and so forth, until I have this inversely proportional relationship. We can also think about the pressure of gases in terms of real-life scenarios. So if you think about pumping up your bike tyres, as you're inflating the tyre, you're doing work by putting in energy, and that's provided to the particles of the gas as kinetic energy. So since temperature is really a measure of the average kinetic energy of a substance, if you increase the kinetic energy by putting in a lot of work, then you increase the temperature of the gas.
Okay, so... excellent, we're just talking about chemistry exam. Fabulous, I'll just keep going then.
The final topic in this paper is about atomic structure and radiation, and the first part of this is common content with chemistry paper 1. You need to be able to describe the modern model of the atom. There's a small dense nucleus containing protons and neutrons surrounded by electrons which orbit at fixed distances, which we usually call electron shells. You should be able to describe the relative masses and relative charges of each of these subatomic particles. It's important the way you see the word relative, you're answering in the form of a number and not just saying positive, negative, neutral. You are allowed to say that the mass of an electron is very small because that's what the specification says, but if you do know a numerical value, it's fine to use that instead. In terms of the numbers of the subatomic particles, you won't be given a periodic table for your physics exam, but you can be given either a periodic table square as part of the examination paper, or the symbol for the element with the mass number and the atomic number printed to the left. The bottom number for an atom is the atomic number, which tells you the number of protons, and that will be the same as the number of electrons in an atom. Then the mass number tells you how many particles there are in the nucleus, which is the protons added to the neutrons. You should know that the radius of an atom is about 0.1 nanometers, which can also be expressed as 1 times 10 to the minus 10 meters, and only about 1/10,000th of the radius of the atom is the nucleus. Atomic structure is relevant because when we're talking about radioactivity, it tends to be different isotopes of elements that we're interested in. Isotopes are atoms of the same element that have the same number of protons and different numbers of neutrons. It's really important that you define them as atoms and that you give the definition in terms of subatomic particles and not just the mass number and the atomic number, which some other exam boards do. The section about developing the model of the atom is introducing the idea that scientists do experiments to collect data and then they update their model in light of that data. We start out with a British scientist, John Dalton, who described atoms as being solid, indivisible spheres. Then J.J. Thomson discovered the first subatomic particle, which was the electron, and he developed the plum pudding model. This was a 3D ball of positive charge with negative electrons scattered throughout it. Then Ernest Rutherford did the alpha scattering experiment, and he's the only scientist where you need to know the details of the experiments that he did. He took a very thin sheet of gold foil and fired alpha particles at it, and what he and his students found was that the vast majority of these alpha particles passed straight through, which was evidence for the fact that the majority of the atom was empty space, and then also a small proportion were deflected directly back, and this was evidence both for the fact that most of the mass of the atom was concentrated at the centre in the nucleus, and also for the fact that that nucleus had a positive charge. Niels Bohr's calculations said that electrons orbited the nucleus at fixed distances, which we now call electron shells. Later, various scientists did experiments which corroborated his findings. At around the end of the First World War, there were experiments that led to the idea that the positive charge of the nucleus could be split up into smaller particles which all had the same amount of positive charge, and we call those protons. Finally, in 1932, James Chadwick provided the evidence to show that there were also neutral particles in the nucleus, which he called neutrons, and these were important because this led to the discovery of isotopes and helped us to explain some confusing data like the relative atomic masses of chlorine and copper. You need to know that some atomic nuclei are unstable, and these will give off radiation as they're changing to become more stable in a process that's random and is called radioactive decay. When we say it's random, this means that we can't predict which nucleus is going to decay at which time. We just have to wait and see. As that decay happens and the alpha particles or beta particles or gamma rays are given off, we describe the rate at which that decay happens as activity, which is measured in becquerels. You can measure this with a piece of equipment called a Geiger-Müller tube or a Geiger counter. All of these different kinds of radiation ionize, which means they turn other atoms into ions by removing their electrons. The first type of decay you need to know about is alpha decay. An alpha particle is made of 2 protons and 2 neutrons, so it's the same thing as a helium nucleus. We start off with a parent nucleus of the unstable isotope, and then an alpha particle breaks off and is released, and what's left behind we call the daughter nucleus. This is going to be a completely different element because it's lost 2 protons, and it's also going to be 4 atomic units lighter because it's lost 2 protons and 2 neutrons. Alpha particles are very ionising, so they're great at turning other atoms into ions. They're not very penetrating and can't pass very far through substances because they're so big that they're relatively easily stopped. They have a short range in air for the same reason, because they collide with molecules in the air and these stop them from travelling further. They can be deflected or pushed to the side by an electromagnetic field, and they can be stopped by a thin layer of paper. Beta decay is also a particle, this time a fast-moving electron. This often confuses people because we're talking about a nucleus, so why would there be any electrons? The best way to think of it is to imagine that a neutron is made out of a proton with an electron stuck onto it. One of these neutrons is going to turn into a proton, and in the same process it's going to release that fast-moving electron. And that's the beta particle. Again, this element is going to turn into a different element because it now has one more proton than it had before. Beta particles are less ionising than alpha particles, both because they're smaller and because they have a lower charge. However, they are more penetrating because they're smaller, so they can get further before they're stopped. They have a medium range in air, and they're still deflected by an electromagnetic field, but they'll be pushed in the opposite direction to an alpha particle, and they'll also be deflected more because they're a lighter particle, so the same sized force can push the particle further. Beta particles can be stopped by thin aluminium foil. Gamma radiation is not a particle. It's a transverse electromagnetic wave. We see it being released at the same time as an alpha particle or a beta particle. Since it's not a particle, when it comes to writing equations, there isn't any difference between the parent nucleus and the daughter nucleus. The gamma being released doesn't change which element something is, and it doesn't change the mass of the nucleus either. Gamma rays are even less ionising than beta particles, and they're even more penetrating. They have a huge range in air, and they can basically move infinite distances in a vacuum. They're not deflected by an electromagnetic field, and they can only be stopped by using thick lead. So an alpha particle can be stopped by paper, a beta particle can move through paper but will be stopped by aluminium foil, and gamma radiation can go through everything up to thick lead. For AQA GCSE Physics, you don't need to be able to predict what the daughter elements are from nuclear equations, but you do need to be able to make the atomic numbers and mass numbers balance. For an alpha particle, this is relatively straightforward. Radium-219 has a mass of 219 and the alpha particle has a mass of 4, so therefore polonium must have a mass of 215 because the two sides of the equation have to add up to be the same as each other. And then likewise radium has an atomic number of 86 and the alpha particle has an atomic number of 2, so therefore polonium must have an atomic number of 84, and I can tell that even without my periodic table. The beta particles tend to be where people fall down. The mass is quite straightforward because for the purposes of this exam we're going to treat the mass of an electron as 0. So the mass of the nitrogen isotope is still 14. But the really common mistake we see is that people will do 6 minus 1 and end up with 5 for the atomic number of nitrogen, which is not correct. If you think about it, the two sides of the equation have to balance. So 6 is equal to something take 1, and the something, of course, is going to be 7. Radioactive decay is a random process, so we don't know which particular nucleus is going to decay, but we do know that for a bulk sample, the rate of decay is pretty much constant. Half-life is the time taken for either the count rate, which is measured with a Geiger counter, to decrease by half, or for half of the number of atoms in the sample to decay. Either of those definitions would take the same amount of time. There are two ways that you can be presented with a question about this, either in the form of a graph or the form of some numerical data. The y-axis of your graph could be activity or count rate or the number of nuclei, but regardless I would handle the graph in exactly the same way. Let's say that my initial activity is 20,000 becquerels. To work out what the half-life is, I'm going to see how long does it take for the activity to fall to 10,000, which is half of 20,000. I could then read off my axis that this took 5 seconds. Now the interesting thing is that you don't actually have to start at your y-axis, because the rate of change will remain constant. I could start at 10,000 and it would take the same amount of time for the activity to decrease to 5,000, and it would also take the same amount of time for it to decrease from 5,000 to 2,500. The only advantage with starting where your graph hits the y-axis is it means that rather than needing to do a subtraction of your x-axis numbers, like from 15 seconds back to 10 seconds, I can just read off the number that I've got to. The alternative is a numerical question, so this is totally separate to the graph, you can ignore it now. If I have a sample with an activity of 64,000 becquerels, which then drops to 4,000 becquerels, and we want to work out how long the half-life is, the first thing we want to do is to write out the numbers and half the activity. So I start off with 64,000, which is halved to 32,000, and then 16,000, and then 8,000, and then finally 4,000. Now, I would really strongly encourage you to write these and then draw arrows between them. And the reason for this is that often people will look at these numbers and think that's 5 half-lives. So they'll do the calculation and they'll come up with the wrong answer because it's not 5 half-lives, it's 4 half-lives. So drawing the arrows helps you to remember to count the arrows and not count the numbers. So I have 4 half-lives, and I said that 4 half-lives is 24 days. So therefore, what's 1 half-life? If I divide by 4, I'm going to get 6 days, and that would be my answer. Radioactive contamination is where there are unwanted radioactive atoms that have been stuck onto something else, so they've made that other object radioactive. And the risk is that at some point they're going to decay, and therefore whatever object they're stuck to would be exposed to that radiation. Now, the exact level of hazard is going to depend on the half-life of those atoms and also the type of radiation that's being given out. If the nuclei have a half-life of 10,000 years, then even if they're stuck on a person, that person is probably quite safe. Whereas if the half-life is a few seconds, they're definitely going to be exposed to radioactive decay. Irradiation is different. It's not the radioactive parent nuclei that are touching you or touching the object that's being irradiated. Instead, the object or the person is being exposed to the alpha radiation or the beta radiation or the gamma radiation that's being given off during radioactive decay. That process could still be hazardous to your health because it might ionise your DNA, which could lead to mutation and ultimately cancer. But the object or the person does not become radioactive. And if they move away from the radioactive source, there's no further risk of injury. Irradiation can be used to sterilise surgical equipment or even produce. It's completely safe to use that medical equipment in surgery because the scalpel hasn't itself become radioactive.
You don't need to know about how a Geiger counter works, no. And likewise, cloud chambers. They are situations where conceivably they could write a question where like they give you a lot of detail and then give you like a suggest question where you have to figure out what's going on with that. But the details of how a Geiger counter works or a Geiger-Müller tube works and how a cloud chamber work aren't in the specification. So that's definitely not something that could come up as like a factual recall question. A while ago, I saw someone sort of saying, oh, if it's 30% maths, then is all the rest of it just facts that you need to learn? So 40% of the paper is pure factual recall. And then there's the application type questions, and then there's also the mathsy type questions. So the proportions are 40% facts, of which 15% is required practicals, although that is averaged across the 2 papers. So you could have like loads of required practicals in paper 1 and none in paper 2. Yeah, so that's basically where we're at. Also, is potato on you India? Oh. Did I go over calculations? I went over half-life calculations. I talked about stacking some different ones together. I haven't talked about the different math skills yet because I'm going to do all the mathsy stuff at the end once we've got through all the physics. It would depend on what the contamination or irradiation question was. I'm kind of dreaming up a sort of evaluate type one where they ask you about which one would be more dangerous. So if you're being irradiated, you're immediately being exposed to radioactive decay, which is potentially going to ionize your DNA and ultimately mutate it and give you cancer. But if you move away from the source, then you're not being exposed anymore. So the hazard is gone. Whereas if you're contaminated, then you're not necessarily being exposed just then, because it would depend on the half-life of the radioisotopes that are sort of stuck to you. But if they're stuck to you or stuck to your clothing or whatever, then you're going to carry on being exposed to radioactivity for a longer period. So I could see sort of like an evaluate question type like that. They could give you questions about uses of irradiation, so things like sterilizing medical equipment I already mentioned, food, where they're like stuff that's stored in cans and things, where they irradiate the cans to make sure that there's no bacteria so that those cans are going to last for a long time. But in terms of stuff that's actually listed in the specification, that's it. So anything else would need to be application type stuff. Yes, if you've got a quick half-life, then what that means is that it's more likely that within a short period, you're going to have radioactive decay. So it's like, if you imagine it like a beat, if something has a short half-life, it's like there's decay, there's decay, there's decay. Actually, I have no idea if those clicks are going to come through on the microphone, but you've got decay happening at quite regular intervals. Whereas if you've got a longer half-life, it means there could be a really long period where there's no radioactive decay. And so, you're comparatively safe, and eventually it happens afterwards. No, I'll do some directly proportional graphs when we get to the end. Contamination. Yes. So contamination is like, if the extended Simpsons credits, where Homer gets like some of the radioactive waste stuck to himself and then he's walking around touching other things. That's contamination. It's where you've literally got the thing that is radioactive transferred onto your body. And so you are radioactive too. Whereas irradiation is where, like, if you imagine irradiation with a gamma source, the gamma rays are passing through you, and so you're being irradiated, but there's no radioactive material actually making contact with you, and so you're not becoming radioactive. Yeah, if it's I wouldn't think of it as contamination, because contamination sort of always sounds a bit accidental to me. But yes, I guess a tracer is an example of contamination, because you are intentionally putting a radioactive source into someone, injecting it into their heart, or putting it into their body somehow to look for a blockage, usually in their heart or in their intestines or things. Yes, uses, just getting onto it.
Despite the associated dangers, radioisotopes can be really useful, and you need to know a couple of things they can be used for. The first one is using them as a radioactive tracer to try to identify where in someone's heart or intestines a blockage is. An isotope that has a short half-life is injected. It needs to have a short half-life to allow the detection of the radiation coming out of the person's body. That radiation is only released when a nucleus decays, so if it had a long half-life, we'd be waiting for a very long time. The isotope is injected and it's allowed to circulate around the body, and it will collect in the damaged area behind a blockage. And then a PET scanner can then be used to detect the emitting radiation. As well as having a short half-life, that tracer is going to need to be releasing beta radiation or gamma radiation, because if it released alpha radiation, that will be stopped by the person's skin, and so even though it was being released, we wouldn't be able to detect it. Radioisotopes are also used in radiation therapy for cancer. Gamma radiation is used to kill cancer cells, and they avoid damaging the healthy cells by firing a sort of focused gamma ray gun from a variety of different angles, in such a way that the cells of the tumour are hit multiple times, but the healthy cells around them are only hit once. Nuclear fission is the splitting of a large unstable nucleus like uranium or plutonium, and it very rarely occurs spontaneously. So for us to be able to harness this and generate electricity, we trigger that fission reaction by firing a neutron at an unstable nucleus. And this will cause the nucleus to absorb the neutron and then to start breaking down. As that parent nucleus undergoes fission, it splits into two smaller daughter nuclei, which are about the same size as each other, and it also gives off 2 or sometimes 3 neutrons, plus some gamma rays, and also some energy is released. All of the different particles that are released from this, all of the fission products, are moving, so they all have kinetic energy. At the start of this nuclear fission process, I provided 1 neutron, which caused 1 parent nucleus to decay. But that parent nucleus is going to produce up to 3 more neutrons, and so in the next round, we can have 3 more nuclei decaying. And then we're going to end up with 9 neutrons, which can cause another 9 nuclei to decay. And you can see how very, very quickly this can escalate, and this is what's called a chain reaction. In a nuclear reactor, that chain reaction is controlled in order to control the amount of energy that's being released. But in a nuclear weapon, or when there's a nuclear accident, there's an uncontrolled chain reaction. And this is what happened in Chernobyl and caused a meltdown. So to prevent this from happening, there are things called control rods, which are made out of boron, and they are able to absorb any neutrons. And when the core starts to get hot, the boron control rods are lowered and they absorb any neutrons and slow down this whole process. And then when the reaction is slowed down too much and everything starts to cool down, then the control rods are raised above the fuel rods again, so that the neutrons can carry on interacting with those parent nuclei and the reaction can start to build up again. In contrast to nuclear fission, where large parent nuclei split to make smaller daughter nuclei, in nuclear fusion we see the reverse. Small nuclei like hydrogen fusing together to make larger nuclei like helium, and this is one of the first fusion reactions that occurs in stars like the Sun. Now, when this happens, it releases significantly more energy than fission, and we would love to be able to harness this to use for making electricity and things, but it's not possible for us to do this safely on Earth at the moment because it needs a really high temperature and a really high pressure to start and also to contain the reaction. Now, you might be thinking, well, if it's impossible to do, then how does an H-bomb exist? How does a hydrogen bomb exist? But what a hydrogen bomb does is it uses a fission reaction to create a really high temperature at the start, and that allows the hydrogen fuel contained in the bomb to fuse together to then do this fusion. But of course, at this point, we're not really worried about it being safe because it's a bomb. Its whole point is to create this devastating explosion and release a huge amount of energy.
Okay, so now for some general bits of advice and then some mathsy skill stuff as well. So I know I keep saying this, but there's always people who don't know. You need to be writing in black pen because your exam paper is going to be scanned. So your paper is not ever going to go near one of the markers. It's just going to go back to AQA. They scan the whole thing and then they send pictures of it to the markers on their computers. So if you don't write in black pen, then it just doesn't scan as well. I would encourage you to use pencil for drawings. The real issue with writing in pencil is that if you've sort of written pages and pages and then you're wiping your sweaty, stressed hands over it, then it tends to smudge. But blue ink is really not good because it doesn't scan very well. Likewise, because of the scanning, you want to stay inside the box on the outside of the exam paper because what they will do is cut the margin off. So anything that you write in that margin is just going to be chopped off and no one's going to see it. And also, if you need extra space, there are extra space pages at the back of the exam paper. Use them. Don't use a random gap somewhere around a question because even though the whole paper will be scanned, your marker is not going to know where to look for things, and they're not going to go through the whole thing because that would take them a long time because the software is really unwieldy. But if it's on the extra pages at the back, then there are people whose job it is to look through those extra pages and go, oh, this is question 4, we'll put it with question 4. I've said this for all the other exams, but really for physics, you've got to watch out for your units. It is so likely that they give you a height in centimetres or a mass in grams, and if you don't convert, then you don't get the marks. But make sure that you do need to convert before you convert. Because last year there were a lot of people who were converting things they didn't need to convert because they were just so stressed about it. So just take your time. If you get an extended response question, you are absolutely allowed to use bullet points, and in fact it's encouraged. There aren't any marks for writing in full sentences anymore. They went out in 2017. So if you do it in bullet points, it makes it really easy for your marker to see where you've hit all the different criteria. If you get an evaluate question, which I would say is pretty likely, particularly for maybe 2 of the ways of generating electricity, something like comparing nuclear versus wind or solar versus fossil fuels. Evaluate means compare them. If they've given you any data, you need to do something with the data. So not just say, oh, this one releases 1 megawatt and this one releases 2 megawatts, but going, oh, this one has twice as much power. So you're actually using that data. And then really crucially, you have to actually write a conclusion. So there is 1 mark scheme for all of the GCSE science evaluate questions. And it says that for level 3, for 5 or 6 marks, you need to write a strongly justified conclusion. So I would literally use the words in conclusion so that it's really clear to your examiner that that's what you're doing, and then just kind of pull together some of the arguments you've made to say, this is why I'm saying that this one is best. Okay, so if you write in friction pen, the issue with friction pen is that some friction pens, the way that you can erase them is that it's heat, and the scanners get really hot. Now, last year, some people got so stressed about this that I did a bit of an experiment and I ran an entire ream of paper through one of our scanners at school to get it as hot as I could, and then did a friction pen test. And it definitely was a lot paler than it should have been, but it didn't erase it completely. So I would say don't stress massively if you've already done it, but if you have other pens, use other pens. Yeah, if you write a method, just make sure that it will actually answer the question. So I would say at the end of it, think about your variables. Think, have you changed your independent variable? Have you measured your dependent variable? And have you compared? Sorry, I just looked at the comments and someone saying about comparisons. Have you controlled your control variables? Have you kept them the same? Yes, absolutely draw a table. Love a table. Easiest way for your examiner to see that you have covered both bits. It ends in about 5 minutes. I'm just doing it into my last little bits. So We mentioned variables. So you modify the independent variable, that's the thing you're changing, and it goes on the x-axis, and your dependent variable is the one that you record on your y-axis. Remember, if they ask you to label x and y, they don't mean write the letters x and y, they mean say what that variable is. So I don't know, put time on the x-axis or put activity on the y-axis. Your control variables make it a valid experiment. So in primary school, we would have said it made it a fair test. We don't use that word at GCSE. But I always tell my class, I'm a control freak. I don't like anything to change. I always have the same colour PowerPoint. I always have the same seating plan because I'm a control freak. So your control variables are the things that you keep the same. Repeatable means that when you do the experiment over and over, you get the same results. Whereas reproducible is what we have if somebody's doing some peer review. So if another scientist is checking over your work, or if someone's doing a similar experiment, it's maybe not the exact same experiment, and they see the same pattern, that's then reproducible. Resolution, so if you've got some equipment, it's the smallest measurement that you can make. So maybe on the ruler that most of you have, the resolution is 1 millimetre, or on the thermometers that most of you have used in school, the resolution is 1 degree C. We like computerized methods because they're accurate, rapid, and sensitive. And if you have a graph that you need to draw and you're drawing a line of best fit, I know that in maths you've been told about lines of best fit being straight lines. In science, that's not what we say. We say whatever the data is doing, that's what your line of best fit needs to do. So say if I had, apologies, I don't have a ruler anywhere near me right now. If you had some data that sort of looks like this, then obviously I would get my ruler and I would do a nice straight line that went through it. But if I had some data that went more like this, then I would do a curve that went through that. No, sorry, PowerPoint hates me. So I wouldn't ever go dot to dot. There is literally no situation that you would ever go dot to dot, but you might have something that goes like that if that's what your relationship is doing, because the whole point of a line of best fit is that it's allowing you to make predictions. So if these are the 6 bits of data that I've actually got, and I then want to know, well, what happens at this value, then I can use that line of best fit to make a prediction. Different kinds of errors. So systematic errors are where there's a problem with your equipment and it's always wrong by the same amount. So if your balance is always reading half a kilo lighter, that's a systematic error. That is in fact what we call a zero error, which is like a subset of systematic errors. So all zero errors are systematic, but not all systematic errors are zero. So if the point where 0 should be is wrong, that's a zero error. If the error is elsewhere, then it's just generally systematic. Then random errors are where either your equipment can't measure well enough to tell you what the true answer is. So when I taught this to my year 11s, I gave them an example. I had a Satsuma on a balance, and sometimes my balance said 80 grams and somewhere it said 81, because really the answer was somewhere in the middle, but my equipment just wasn't precise enough. Or it could be something where the true value is changing. So something like the temperature in a room, sometimes it's 18 degrees, sometimes it's 19 degrees, and it's just fluctuating. So if you've got a systematic error, then you need to figure out how much it's out by, and you need to calibrate your equipment. If you've got a random error, then you do multiple readings, so you repeat and you calculate a mean. There's never a mark in GCSE Science for just saying repeat, it's repeat and calculate a mean. And when you do that, you want to watch out for any anomalous results. So those are results that don't fit the pattern, they don't match the rest of your data. Okay, maths requirements. So these are they. So this is going to make up 30% of your GCSE Physics. So are you okay recognising decimals? So this could be something like a scale where you're having to read off the intermediate bits. For foundation, they tend to be quite nice. But for higher, you could have something where we've got 1, 2, 3, 4, 5 divisions, and then this is 1, and you're expected to work out that in between would just be 0.2. It could also be giving you values that are given in decimals. So I don't know if we sort of say, oh, this thing has a mass of 2.3 kilograms, and then the height is going to be 3.2 meters, and doing a calculation based on that. Standard form, please double check your calculator, double check that you know how to do standard form. If you don't know where all of your calculators are going to have a button that probably looks like that, or I have a Temu calculator that has a button that's like that, and that will do your standard form for you. If you don't have one of those, just make sure that if you're going to write a number in standard form that you're then going to use in a calculation, that you put brackets around it. Because otherwise what ends up happening is, say if I have no idea what this calculation would be, but we'll just go with it. If I did that calculation without using the brackets, then I would end up dividing by 2.1 and then timesing by 10 to the minus 2. So yeah, definitely use brackets or just use your EXP button if you have one. Ratios, you've already had some ratios in chemistry. Fractions, we should be fine with. Percentages. If you're trying to think about a percentage, think about the fact that imagine that you've got your mock exam paper back, and if you're doing combined science, it's out of 70, and let's say you've got 50 out of 70, and you would write it like that. And obviously that out of line there, that's a divide sign, right? So I would do 50 divided by 70, and then if I wanted to be a percentage, I'm going to times it by 100. Why did my brain just go to efficiency? Oh, I know. With working out percentages and things, very relevant to efficiency, just remember that if you are working out the efficiency of something, it's going to be useful divided by total, not divided by wasted, because that's a really common mistake. Estimates, we've already had one estimate in the triple chemistry with the how many times bigger is the, or how many times smaller is the nucleus of the atom compared to the atom. Significant figures, so let's just give ourselves a nice number. If I'm asked to give this to 3 significant figures, 0 doesn't count as a significant figure until the real numbers start. And then if I'm looking for 3 significant figures, I'm going to look for the 4th number. So 1, 2, 3, 4. If it's bigger than 5, I'm going to round up. If it's less than 5, I'm going to round down. So this would be 0.238 to 3 significant figures. Means, add them all up and divide by how many there are. Medians, the middle number, so put them in order, and then pick the middle. Modes, the most common. You're way more likely to get mean than anything else. Frequency tables, bar charts, histograms. So bar charts are for categorical data. If they ask you why a bar chart is not appropriate, it's probably because your data is not categorical. Scatter diagrams for continuous data. I literally can't think of a single example of where you would use a histogram in a physics exam, so let's not worry about it. Orders of magnitude. So if I've got a number like that, and then I've got a number like this, then I would say that this one is 1,000 times smaller than this one. That's orders of magnitude. Just sort of with an order of magnitude, it's not an exact number of times it's bigger or smaller. It's like if it's 10 times bigger, that's 1 order of magnitude. If it's 100 times bigger, it's 2 orders of magnitude. Equals, I really hope we all know what it means. Less than, this one is a lot less than. So say if you were comparing the size of a bacteria to the size of a human, this one is a lot bigger than, just bigger than. This one is directly proportional. Oh yeah, someone asked about directly proportional graphs. So apologies again for my lack of ruler. So this graph is pretty much directly proportional. And the reason that I know that is that if I double my x-axis, let's make this, if I double my x-axis, so from 5 to 10, then I also double my y-axis. Okay, that's what directly proportional means. And I can identify that this is directly proportional because I have a linear graph. So this is going to follow y equals mx plus c. But actually, my c, my intercept, is the origin. It's 0, 0. Okay, so if they ask you whether a relationship is directly proportional, pick 2 numbers where we're doubling and see does your y-axis double as well. Obviously, it doesn't have to be doubling if you haven't got the option of doubling. If this was to triple, then this would also need to triple. Changing the subject. So I mentioned before that you don't necessarily have to change the subject before you substitute. So if we gave you something like this and we said we wanted to work out what's m, and we told you that the amount of kinetic energy was 1,000 and the velocity was 10, then you could write in, I'm running out of space here, you could do 1,000 is half times m times 10 squared. So 1,000 is 50m, and then divide both sides by 50. you're absolutely allowed to do that. You don't actually have to rearrange this first and say, oh, actually, m is going to be 2ek over v squared. You can do it that way around, and I would probably recommend doing it that way around if you're going to go on to A-level physics, but for GCSE it's okay. Substitution is what we've just done there, so putting the different numbers from the question into the equation. So I would always recommend that you write out the equation in full, even though you're pulling it off the equation sheet. And then if you're not sure about what things are, if it doesn't say this is the charge, this is the potential difference, look at the units. Solving equations is just doing what we've carried on doing there. So I substituted in 1,000 for EK and 10 for V, and then I've sort of expanded things and worked it out. And then converting between graphs and tables is just, you know, they're going to sort of give you, what could it be? Oh, here's the potential difference, here's the current. So, you know, we've got all that lot, and we're saying, okay, this is going like this. Wait, hold on. That was bad. Brain not working. Try again. That's what we want. Then getting our thing and going, okay, right, so I'm going to put one cross there, I'm going to put one cross there, and actually plotting the data. You should be able to convert. So these prefixes like milli and micro and nano, they can apply to any base unit. So you can have milliamps, or you could have microvolts, or you could have nanowatts. So all of the conversions are thousands. The only exception is centimetres, and the reason it's an exception is because it's not a proper scientific unit. But hopefully you know that there are 100 centimetres in a metre because you use them all the time. Okay, that has covered all of that lot, so I'm going to have another little look at the chat and see if there's anything else that anyone else wanted me to cover. Oh, quite a lot in the chat since I last looked. Do we need to bring thermometers? Okay, right. Can you say... Why does total resistance decrease in parallel? Okay, so think of it like, have you ever seen gladiators? And there's the gauntlet, and you're trying to push through the gauntlet. So the components are like, they're providing the resistance, right? They're the gladiators. They're trying to stop you going through the gauntlet, and they're able to stop a certain number of people. But if we suddenly let some of you run around the gauntlet rather than running through it, then they're less able to resist you. It's kind of splitting them up so that they have less impact on you. Is exam QA even helpful? Don't know what that is. Where can I buy a thermometer? Don't need a thermometer. Do we need to... Okay, if they don't... AQA for GCSE, they only give you marks for rounding to an appropriate number of significant figures if they've told you to do it. For A-level, they just expect you to know. But the rule is the number of significant figures in the question is the number you need to be using. So say if we had a question and we were working out, I don't know, we were working out gravitational potential energy is mass times gravitational field strength times height. And if we'd said to you, oh, this object has a mass of 72.5, that is a 7, honest, and gravitational field strength is 9.8, and the height is going to be this many meters, because the smallest number of significant figures in my data is 2, I would give my answer to 2 significant figures. Does physics have the least content? It feels that way. At my school, we finish physics in sort of February. Could uncertainty come up? Yes, it could. So uncertainty is the spread of values around the mean. And AQA make it actually really easy, and it took us a little while to realise they made it so easy. So let's say we've got some different bits of data that they've given us. We'll put them in order for you, will be nice. Okay, so this is the data, and they ask me, they want the mean and they want the uncertainty. So first thing I'm going to do is get rid of the anomaly because it's wrong. It's very, very different. Next thing I'm going to do is work out the mean. So I would add all that lot up, and I would divide by 5 because there's 5 of them left, and I would get 7. And then my uncertainty, I'm going to do, what's the range? So the range is 4. And then what's half the range? So 4 over 2 is 2. So I would say that my value is going to be 7 plus minus 2. So a little plus minus sign. So that is going to be half the range. Technically speaking, it should be about displacement from the mean, but the last few years AQA have always made it so that it's half the range. So we define uncertainty as the spread of values around the mean. Well, Linus, I agree with Mr. Dickinson. Tangents. Okay, I can go through tangents, but I would be surprised to see them coming up on paper 1. Nope, quadrats is biology paper 2. Okay, right, we'll have a quick look at tangents, but I need to find a ruler first. A straight edge. This'll do. Okay, so let's say that I have got some data and it's giving me a line of best fit like that. And okay, let's say that this is topping out at 100 and this is 10, right? If I wanted to know what the mean gradient was, then I would do rise over run, change in y over change in x. I'd do 100 over 10, and that would give me 10. And I would just have compound units based on whatever this was. So I don't know, like if this is joules and this is time, then it would be joules per second. So the reason you draw a tangent is if we want to know actually what is the gradient right here, or what is the gradient right here. So then I would take the longest ruler I could find and draw, this is really hard to do on this, and I would draw the longest straight line that I can do. It should be touching the curve in just one place. I have completely failed, but that's because I don't have a piece of paper. And then based on that, I can then work out my new value of my change in y and my change in x. So I'm totally eyeballing this, but that would be, I guess, about 50, and that would be about 3. So then I'd have 50 over 3, which is a number, 16.7, I think, which makes sense, right? So this was my overall one. This bit of the graph that's much steeper has got a much higher gradient. Okay, so it looks like that is pretty much all the questions. Oh, I've got some people wanting half-life again. Okay. Very quick half-life. So if we've got some numbers, let's say we're starting at 2,560 and we are finishing at, oh, brain is not working. No, in fact, let's start with some easier numbers. Oh no, I think we can do that. Okay, so let's say, let's make it 256, and we want to know how many half-lives does it take for the activity to drop down to 2. So we're going to say, what's half of 256? It's 128. Hello, computer scientists. What's half of 128? It's 64. What's half of 64? It's 32. What's half of 32? It's 16. What's half of 16? Running out of space, it's 8. And down to 4 and down to 2. All right. So each time I'm just halving it. Right. So I've done it once, twice, 3 times, 4 times, 5 times, 6 times, 7 times. So if we then said, well, that process took 14 years, then that would be 7 half-lives. So therefore, 1 half-life would be 2 years. The other thing they can do is, instead of giving you numbers, they give it to you on a graph. So say we've got 10,000 up here, and they just give you a graph that looks like that. And you go, okay, well, if that's 10,000, then here's 5,000. How much time did that take? And you would literally just read it off the graph there. Look. 30 seconds or whatever it says. Technically speaking, your line of best fit should only fit within your data. So if you've got a cross that's here and a cross that's here and then some stuff in the middle, then your line of best fit should go from there to there. It shouldn't actually be down here and it shouldn't actually be up here. Really for GCSE, nobody's going to have too much of an issue with it. But what you mustn't do is try and force your line through the origin if it doesn't go there. So like if we have, say if we had some data that went like that, our line of best fit should go like that. If it went like that, that would be okay. What it definitely can't do is go like that. Obviously, that's a very extreme example, but I've seen people do things on that sort of thing. Yeah, if they ask you to add something to a circuit, then you do just draw on top of it. They're not going to ask you to add a resistor to a circuit because obviously we talked about this already. We've got a straight line. If I just drew a resistor on top of it, then that's not a resistor. It's a fuse. But yeah, like if they give you a circuit and sort of say, I don't know, like where does the ammeter go? It's fine for you to do that on top of the line. Okay, right, back to a bit of series and parallel. I think at this point, folks, we're just covering stuff that we have already covered, which is fine for a little bit. But if you don't have any questions and you want to disappear, I'm not going to be offended. Good luck for tomorrow, and I really hope it goes well for you. Okay, so this is a series circuit. And here is the world's dodgiest parallel circuit. Obviously, we are using a ruler. Obviously, we are making sure that there are no gaps between any of the lines. Okay, so if I take my ammeter, so ammeter is for current, right? And I measure the current here, it's 3 amps. If I measure the current here, it's 3 amps. If I measure the current here, it's 3 amps. It's going to be the same everywhere, right? So imagine that you've got a traffic jam. You've got these little electrons, they're cheerfully moving along, and every electron is as close to the one in front and the one behind as it can be. So as soon as one of them moves, the other one moves. And so that means the speed is the same everywhere. Whereas if I've got my parallel circuit, then we start off and over here we've got our current of 3 amps, and the current is basically how many coulombs of charge are passing a point per second. So this means that every second 3 coulombs of charge go past. But when we get here, some of my electrons go this way, some of my electrons go this way. So since these are 2 identical branches with identical light bulbs, you can obviously tell they're identical. They're absolutely perfect. We're going to have 1.5 amps going this way and 1.5 amps going this way. If I had a slightly funkier parallel circuit, maybe this one's got a resistor in it as well. And I don't know, this one's got a variable resistor. So we've still got 3 amps here. But let's say that going this way, here we've only got 1 amp. Right, I wouldn't know that just from the picture. I'm just telling you there's 1 amp. Well, in that case, if I did it on this branch would be 2. Okay, so it's not always going to split half and half, but it is always going to split so that these 2 add up to be what this is. So that's current. And then for potential difference, what have I just done? That was not meant to be an ammeter. For potential difference, that is going to be, it's the difference between 2 points. So it's saying about how much energy has been transferred. So, oh my goodness, the drawing skills are failing this evening. Okay, so let's say that here we've got a voltmeter and it's measuring 12 volts. So that means that there's, as the charges pass, we've got 12 joules being transferred. So my little happy electron comes along, and it comes along to this branch, and it's going to give all of that energy to this light bulb here. So if I took a reading here, that would also be 12 volts, because it's not going to go to this light bulb. It's just going to go past this one and go right back to the cell. And then any electron that goes this way is going to give all of its energy to this one. So this one's also going to be 12 volts. Whereas in my series circuit, my little electrons come along. So let's say it's the same thing. This is still 12 volts. It's going to give, if these are identical bulbs, it's going to give half to this bulb, and it's going to give half to this bulb. The symbol for an LED is going to have lines going off it, arrows going off it, because the arrows represent light. So if they ignored references to limit of proportionality, that wouldn't be because it's from paper 2, that would be because it's not relevant to that particular question. So you're very unlikely to get, for physics especially, you're very unlikely to get anything that's really paper 2 content coming up in paper 1. It's much more likely to happen the other way around, because in physics they specifically shout out the first 3 units as fundamental concepts that can be examined in paper 2. But like obviously sort of the Hooke's law spring practical, there's ways it could be in each, because you could talk about the elastic energy that's stored in the spring. I don't know the specific question you're talking about, but if they said to ignore references to it, it would just be because it's not relevant to that question. Righty. Radioactive half equations. Okay. Right. So we've got 2 different styles of half equation. Oh, I shouldn't do the alpha, should I? I should do helium, because that's what you guys are meant to know. My bad. I'm tired. Okay, so if we have, let's just make life simple for ourselves. This is not a good isotope for this, but I'm just going to go with it anyway. Say I've got oxygen breaking down and it's losing an alpha particle. I'd say, right, this side of the equation has to add up to the same as this. So this is 18, so this is going to be 4 plus 14. And then likewise down here, if this one's 8, this is going to be 2 plus 6. And I know, because I teach chemistry as well, that is carbon. You would not be expected to know that was carbon. You would be told what the daughter element was, or just told it doesn't matter. And then if I take that same isotope and I have a beta particle being released, same thing. The left side of the equation must equal the right. So if this is 18 and this is 0 plus, it's still going to be 18. This is 8 minus 1. So something minus 1 is 8. So that's going to be 9. So that's going to be hydrogen, helium, fluorine. Yes, I'm reading the comments. How do you think I'm responding to you? I'm literally sat here looking at my phone going, what else do they need? None of the stuff we've done recently has been triple. So the video as a whole did cover everything that you needed for the triple exams. If you're going back and watching it, the bits where it goes dark purple at the top and it says triple only physics, they're stuff that's not in combined science. Fusion versus fission. Oh my goodness. Could you guys not turn up earlier when I was going through this stuff? Do I put in the bottom number? As in the equation, do I need to write the bottom number? I do need to write the bottom number. Right, so fission. We had, fission is where we've got our unstable nucleus, and it should be different colours, but it's not now. And we're going to have a neutron coming along, and the neutron is going to bash into it, and it's going to split apart into 2, hopefully more stable daughter nuclei. How did I draw 5? And that one's going to be 6. So neutron comes along. Oh wait, hold on. I need some more neutrons here. My bad. So this is my parent. This is my neutron. These are my daughter nuclei. And then we also have 2 or 3 more neutrons. And also a ton of energy. Whereas with fusion, that's where we're going to have smaller particles. So say we quite often have maybe hydrogen 2. So we can have a couple of bits of hydrogen 2, and then they are joining together to make helium, which is what happens inside a star. But it takes a huge amount of energy to make it start, which is why we haven't managed to do it on Earth yet. So it releases loads of energy, which is why stars are shining. So the only way we can really make it happen on Earth is by using a fission reaction to start the fusion reaction, which is what you do in a hydrogen bomb. But it's super, super dangerous. But we don't care if it's in a hydrogen bomb, because the point of a hydrogen bomb is to blow everyone up. Yep, Aisha's definition sounds pretty good. So fusion doesn't have to be, oh, hold on, she's written helium combined to make hydrogen. Other way around. Hydrogen combined to make helium. So that's what's going on in our sun at the moment. Fusion can be heavier elements. So like in a supernova, you get heavier elements fusing together. But it's just that the hydrogen helium one is the really, really common example. A neutron is fired into a uranium-235 nucleus. This causes the heavier nuclei to split into a chain reaction. Okay, so the one thing I would say for heme is that the process of it splitting is not a chain reaction yet. The reason it's a chain reaction is that now I've got 2 neutrons where I started off with 1. So that means that these 2 neutrons can go on and cause 2 more nuclei to start splitting. And then they're going to spit out another 2 neutrons each. And so that can then cause 4 to decay. So that's where the chain reaction aspect comes in. This first bit where it splits, that's not a chain reaction. Right, I think people have pretty much stopped asking questions. So thanks very much. Yep, you do know there's a few other things on the channel if you're still revising this evening. Obviously get some rest. But the recall questions, they are point-by-point questions going through the spec saying, do you know the units for this? Do you know what this is? Can you define this thing? There's some stuff in there, because I wrote them before the equation sheet was given to you, like I wrote them back pre-COVID, there might be some stuff in there that you don't actually need to have memorised, but they're pretty good. The 6-mark challenge is lots of extended response questions. So the first however many weeks it is, there are 6 videos per week, and the third one is physics paper 1. It's pretty obvious because they're all red for physics, and yeah, it's basically number 3, number 9, and number 15, blah, 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 blah. And then this video here is just some like last minute advice about things to do when you get in. So things like writing down all your units first and writing in black ink and that sort of stuff. So if you have got any other questions, there is both this talk, the version I recorded in 2023 and 2024, the full video is already available. I think you should be able to skip back in the live stream, but I'm not 100% sure on that. But even if you can't, the 2023 and 2024 versions are there. So good luck for the exam, guys. Thanks very much for joining me. And yeah, I hope it goes really well. And I hope to see you back for some biology revision after half term.